Everything that we do in scientific research has a degree of uncertainty, and such a young research field as microplastics pollution is not an exception. The fact that plastics are all around us, in seawater, fresh water, in soil, in atmosphere, in sediment, that they're chemically diverse and complex materials and come in a whole range of sizes and shapes does not make microplastics research any easier or certain when it comes to quantifying and characterizing these contaminants in the environment. Because microplastics research is a relatively new field, we're still figuring out the best ways to collect and analyze our samples, and therefore to reduce the uncertainty of our knowledge, measurements, and predictions. The smaller the particles, the harder it is to collect, detect, and identify them in a wide range of environmental matrices, the more sophisticated tools we need, and the higher the risk of contamination is, and therefore the higher the uncertainties. Methodologically, the uncertainties are encountered at every step of microplastics research, from sample collection, for example, where, how, and how frequently we collect the samples, to sample processing, for example, what the effectiveness of different extraction methods of microplastics is, to analytical measurements, are we using the most robust and accurate and precise tools, to data analysis and interpretation, both of which will involve making assumptions and extrapolations. It is a lot of uncertainties to take care of, and the key is being aware of what these uncertainties are and try to minimize or where possible to avoid them. Practically, the best way is to plan the research ahead so that the analytical targets are known and the best way to collect them is identified. Analytical tools have their own uncertainties, and we need to know how to optimize our sample and sample checks, like using monitors, for example, to ensure the best output of our data. Challenges need to be foreseen and compromises need to be made during the process, and this can be related to cost, space, resolution, both in time and in space. Important is to be transparent about every step that has been taken to produce a sample and generate a number. This will help the user, the scientist or modeler, to make their own conclusions on whether the dataset is robust enough for the intended purpose. Quality assurance and control are in the center of good practices in microplastics research. We ensure the quality of sample collection, preparation, and analysis, and this involves strict contamination control and monitoring by taking procedural blanks at all steps of sample collection, handling, processes, and analysis. This, for example, involves working in clean conditions, such as clean and air quality controlled laboratory, using adequate and clean labware and reagents, ensuring that our labware and consumables are fit for purpose and deliver best signal, the latter is in relation to measurements. Where possible, we monitor the effectiveness of the sample preparation for analysis, for example, by using yield monitors. When conducting measurements, we also ensure that the signal, a signal of detection quality, is optimal and cost and time effective. We correct our measured data using blank and recovery values, the latter when possible, and we propagate non-analytical uncertainties throughout calculations and extrapolations. However, when it comes to modeling or predicting plastic abundance and distribution in the environment, it is important not only to optimize the quality of the measurements that we make, but also to account with most certainty for processes that control the presence of plastics in different compartments and the scale at which these processes happen. And this concerns the supply rates of plastics to the environment, the interactions with biota, with physical and biogeochemical processes, transport pathways of these contaminants to the environment and within. For example, how long do plastics stay in the surface waters? What are the major processes that remove them from surface to depth, and how quickly they occur and what they are influenced by? Assumptions and extrapolations are required for both measured data and model data. The key is to know the nature of such assumptions, their limitations and benefits. Uncertainty of the measured data and processes must always be considered and accounted for when using or validating models. Ultimately, the models are as good as the data you're testing and validating your model with. Even if uncertainties of models and measurements are large, it is still useful to have such models and measurements, as it all depends for what purpose the models are used for. Generally, the uncertainties and their nature set up the pathways for improving both quality of measurements, parameterization of processes, and the ultimate model predictability.